What we know in general for the variance is we know that the variance is bounded by n divided by log n, and it's bounded below by c times log n, and this one is in dimension 2. And remember, this is compared to the expectation. We should compare this to the expectation that the variance of the passage time is of order. So let's say it's bounded above and below by a constant times n to the 2 chi. Another constant times n to the 2 chi, where here chi is dimension dependent, but it's supposed to be less than 1. And for d is equal to 2, it's expected to be equal to 1/3. Okay? So today, we're going to look at this upper bound. So today, we talk about variance upper bounds. Okay? And our goal will be, our first goal will be to prove a result due to Krishnan in the 80s. I don't remember exactly when he proved that the variance is bounded by n, so constant times n. So this is the order that we would get if we were looking at a sum of independent ID random variables. And it makes sense that the passage time would involve about n steps. You know, it would involve at least n steps, but would involve order of n steps. And then along a fixed path, we have independent random variables. So in that case, we would get a variance of n. Of course, you were taking an theorem that makes the problem nonlinear and much more complicated. And we know, or we expect in the end, that this will actually change the order of the variance. But perhaps the first step, that's the step that Krishnan took, would be to just actually get a bound of constant order times n. Okay, so both for Krishnan's theorem and also all known results, actually both for the upper and lower bound, but especially the upper bounds that I'm going to discuss, they involve three main ingredients. And those are, first, we're going to need to look at how the passage time changes when we change a single edge. So this is what I'm going to call the linearization of the passage time. And this means we want to know what t, and here I'm going to think of t as a function of a fixed weight. And then, so this is a fixed weight of a given edge. And then, as a function of the collection of weights for all other edges. And I'm going to think of changing only the weight of a single edge, and I want to know how does the passage time react to making such a change. So this will be, understanding this quantity will be an important part of getting this bound and actually also the improved bound with log n in the denominator. Then number two is we'll need moment bounds of geodesics. So I very casually said that when we look at the sum, when we look, at the definition of the passage time from 0 to any 1, we'd expect this to contain, we expect any geodesic, any path that's relevant to this minimization to be of order roughly n. And so that's something that we will want to quantify, and quantifying this will be part of getting a result. And finally, and the input here will be, actually, that's the main thing that Krishnan contributed to this problem, and that's this lemma that was mentioned yesterday that we'll look at in detail. And another ingredient, the final ingredient that will appear in various forms, including in a refined form to get the improved upper bound, will be the fact that geodesics are roughly one-dimensional. So we'll have to make sense of this when we get to it. But these three ingredients are actually the only things that we'll use. What we'll see is that the types of tools that we use to get the upper bounds don't usually use that much information about them all. Really, the only things that we use are the only information about them all is contained in these three three ingredients, and B and C are actually closely related to each other. So we don't really have a good way to exploit so much information about the actual model that would allow us to, and perhaps that's what's required to improve the estimates that are known for the variance. And as a consequence of this, or maybe a manifestation of this, the way that we actually bound the variance is by using very classical tools from concentration of measure. Where's the eraser? And the first tool that we're going to use, forget this Krishnan now. Krishnan didn't call it this, but it's essentially nowadays called the Efron-Stein inequality. It's just a very general method to estimate the variance of a function of many independent random variables, like the passage time. Okay, so the main tool is the Efron-Stein val. And what it says is the following. We're going to give ourselves a function from R to the N to R. And functions, random variables xi, I between 1 and n, and xi prime between 1 and n. And what do we want to know about these? We want these xi to be independent, and also independent of the xi prime. So these are independent across all indices, and xi is also independent of the xi are also independent of xj prime as a family. And xi has the same distribution as xi prime for all I between 1 and n. And in this case, the Efron-Stein inequality tells us that the variance of x1 of f as a function of these random variables is bounded by a half times the sum from I equal 1 to n of the expectation of something that looks like a derivative. So what we do is, one step at a time, we consider the function f as a function of the entries. And in the ith summand, we're going to replace f here by f with all the same entries, except for the ith entry replaced by this independent but identically distributed copy of xi. Okay? So of course we're going to want to apply this result to f being the passage time and the xi's being the weights. And when you look at the right-hand side here, you can see how number A here is going to be relevant. So first, before we apply it to the passage time, let's look at how this is proved. This is very easy, but it turns out to be very useful in many situations. Any questions about the statement? Okay. All right, so we're going to think about successively revealing f as a function of the entries. So for that, let's introduce some filtration. So f0 will be a sigma algebra, just the trivial sigma algebra. So the sigma algebra generated by the entire set and the empty set, and then fi for I between 1 and n will be the sigma algebra generated by x1 up to xi. So we reveal x1 up to xi. And then we're going to define delta I to be the conditional expectation of f with respect to fi minus the conditional expectation of f with respect to fi minus 1. So because here, just to be perfectly clear what's going on. Because here we're actually looking at a function of independent entries, this conditional expectation just means that we fix x1 up to xi, and we integrate out the remaining random variables. Okay, so this is the integral of f of x1 up to xi, and then maybe let's use a different notation here. Okay, so this is our definition for delta I. So these guys, the delta I, are Martingale increments. So in particular, because they're Martingale increments, they're uncorrelated, right? So that means that when we look at the variance of our function, the variance of the random variable, we can write it as a sum of the variances of these increments, right? Okay, so this is equal, actually, to the sum I equal 1 to n of the expectation of delta I squared. Is this okay for everyone? Okay, so now let's just rewrite this delta I to bring it into a form like what we have on the right side here. So delta I is, we can write as f minus the expectation of f integrating out the ith variable with respect to fi minus 1. So if I look at this here in this first expression, this first conditional expectation, I reveal x1 up to xi, and I integrate out the remaining random variables. Out here, I reveal x1 up to xi minus 1, and I integrate the remaining random variables. So the difference between this one and this one is that in this one, we reveal everything, including xi minus 1, and in this one, we've integrated one more of the variables. Okay, so we can write this delta I as f minus integrate one more of the random variables, fi minus 1. That's okay? Okay, so
does delta I depend on fi minus 1 or on fi?
does delta I depend on fi minus 1? What does that mean? So
is delta I measurable with respect to fi minus 1 or only?
So it's only with respect to fi because it still depends on xi. Does it, maybe, did I get it wrong? Oh, maybe you're right. I think maybe this should be fi. Yeah, thanks. Does that make sense? Okay, thank you. So this is fi. All right, so now what do we get from this? Let's plug this expression into the
E sub I is E sub I expectation.
Yeah, so this is just you take f and you integrate only with respect to the ith. Okay, so as a consequence of this, we get that when we look at the expectation of delta I squared, we can use Hanson and bound this by the expectation of f minus the expectation I of f squared. Is that okay? So this is by Hanson's inequality. Okay, so now let's take this and so far what we've proved is that the variance of f can be bounded by the sum I equal 1 to n of these partial variances, f minus expectation I f squared. And now if you want to write this to rewrite this to match this form here, we can just use a general fact, which is that for any random variable, if you want to know the variance of x, so here this is the variance. We can think of this as the, integrating in two steps as the partial variance of f with respect to expectation of, with respect to the ith entry. In general, when you have a random variable, the variance of x can be written as 1/2 times the expectation of x minus x prime squared, where x prime is an independent copy of x, right? right? And so that's the remaining ingredient that allows us to rewrite this side, the final right side here, into this form. Okay, so let's formally apply this Efron Stein to the passage time. I'm saying formally because I don't want to worry about the fact that n here is potentially, the way we proved it is n was finite, but I will leave it to you. Maybe I'll put this as an exercise to extend this if necessary. So let's just formally take this result and set f to be equal to the passage time from 0 to NE1 and see what we get. So we want to apply with f, equal to the passage time. So again, there's a little difficulty here because in this case, n is infinite. So maybe I'll leave this as an exercise. I know I haven't written down an exercise sheet yet, but there'll be many exercises in this lecture. I guess I'll collect all of them into a sheet that we'll be discussing on Friday. So let's apply this. Let's not worry about this, and let's just assume that everything works as expected and apply this with f equal to the passage time. And then the Efron Stein inequality would tell us that the variance of t is bounded by 1/2. And now the sum, remember, was over the random variables, right? The random variables that are the input of t. For the passage time, those random variables are indexed by the edges. Okay? So this is a sum over edges. Okay. If you don't want to worry about n being infinite for this lecture, you can just assume that you're in a situation, for example, where the edge weights are bounded away from 0 and bounded above. Okay, so then everything will take place, all the action will take place inside of a big box because the minimizing path cannot leave this box. So let's look at this. And on the right side, we have the passage time as a function of the edge E and all the remaining edges, minus the same passage time as a function of the edge E, but the weight at the edge E, but take an independent copy of the weight and fix all the other weights. And now, as I stated before, you can see that if we're going to use this, we need to understand what happens when we change the weight of a single edge, what happens to the passage time. As we need to understand this linearization, and as we progress, we'll see that to get the improvement on Krishnan, to get this improved bound of n over log n, we'll have to use a slightly more refined description of this linearization. But for this part, for the application of Efron Stein, it'll be enough to just think a little bit. It'll be enough to just write down something quite basic, a quite basic estimate for this difference. So this is the ingredient one, the linearization. Let's examine what happens when I plug in for a given edge E. So maybe this is 0 and this is NE1, and I'm examining a fixed edge E, and I want to know what happens when I change the passage time from, say, S, some value S less than T, and I change it, say, upwards to T. Okay? How does the passage time change? And the claim is that I can bound this above by T minus S. I guess I don't need this plus because I'm assuming that T is bigger than S, times the indicator. Let me give myself some room here. Times the indicator that the edge E is in a geodesic, or is actually in every geodesic from 0 to NE1 in the configuration where the edge weight at E is equal to S. Okay, so let's write what I just said. So this indicator here means the following. I'm saying that I can bound this above by 0 if this is not, if the condition on the right side is not satisfied. So this is 1 if E is in every geodesic, so every minimizing path from 0 to any 1, or from the origin to any 1, in the configuration S, and then all the other edge weights are fixed anyway. Okay? So why is this true? The first observation is just thinking about why we have this indicator. Let's draw a picture. So suppose you're looking at the geodesics, and then maybe we have a discrete situation where there are 3. Okay, so suppose at S, so when the weight of the edge E is equal to S, this is the situation. There are 3 geodesics going from 0 to any 1. And now I want to know what happens if I increase the weight of E, right? If I increase the weight of E, these 2 paths are no longer geodesic because the path out here did not change, its weight did not change. And so these 2 drop out of the competition, okay? So this shows you why you need this indicator. Unless at the lower weight, E is in every single geodesic, in every possibility, then changing the weight at E has no effect, right? Clearly, if E is in no geodesic, increasing the weight will have no effect, right? Say, for example, if E were over here, and these are the geodesics, if I change the weight at E, it's not going to, if I increase the weight at E, if I decrease it, it might actually help me, but if I increase the weight at E, it's not going to change anything, right? But even if it is in some geodesics, but not in every single one of them, then increasing the weight of E will not have an effect. Okay? So that's the reason we have this indicator. And then what about this? Well, clearly, when we change the weight from E to S, we can only change the total passage time by at most T minus S, right? Okay. So now that we believe this, let's take it and plug it into here. Any questions so far? Okay, so let's use this result. So we now have that the variance of the passage time is bounded by 1/2 times the sum over the edges of the expectation of this T. Okay, already let me start by, before reproducing what we have over here, let me examine what happens when I actually plug in this linearization. So let me look at TE minus TE prime, TE complement squared. Okay, so I want to be able to clearly use this result. So I'm going to split this expectation into two possibilities that have the same mass in the sample space. I can assume that TE is bigger than TE prime, right? Because the opposite situation is just the complementary situation is exactly analogous. So I'm just going to bound this by twice the expectation of TE complement minus TE prime E complement. And here we have a square. I'm going to add the condition, maybe let's just write it like this, that TE is bigger than TE prime. So that I'm exactly in the situation that I have over here. I can just replace this by the upper bound. Okay, so now let's do this. Let's replace it. Okay, so it ends here. Let's replace this by the linearization. And we get that the variance of T is bounded, the 1/2, I guess, cancels with a 2. And so we have a sum over E of the expectation of TE minus TE prime squared, indicator that E is in the intersection of all geodesics between 0 and any 1. And then I'm going to drop the indicator that TE is bigger than TE prime. Okay. Or I guess I can just leave it for now for one final step, so I can get rid of the E prime. TE is bigger than TE prime. Okay, so what do we do now? Let me just use this condition here to drop this minus TE prime. And the reason why it's actually so very important to drop it in this situation, we could have managed it otherwise, is we want to avoid using any minus. We want to decouple this from this indicator. Okay, so let me first do it, and then once it's done, I think things will be clearer. So I'm dropping this minus TE prime. I get TE squared, and then E is in the intersection of all geodesics, like this. Okay, so now we have two quantities, TE squared. So this by itself, if we didn't have the indicator, that wouldn't be so good, because then we'd be summing over potentially either infinitely many or actually, order n to the d edges. So we really need to keep this indicator around. On the other hand, it would be much easier, life would be much easier for us if we're able to separate this TE and this indicator. And that's the reason why I really want to have TE here, because if you remember this indicator, what does it say? This indicator refers to the configuration at the lower value, right? And the lower value, for the lower value, S is equal to TE prime, which is independent, right? So in this indicator, we don't have TE, right? The edge weight TE has disappeared, right? Because inside this, so this is actually a function of TE prime. So that's really nice, because then we have two independent quantities, right? We can just write an equality, a product. We'll have the probability that E is in the edge, is in the intersection of all geodesics, and something that will be a constant, because we assume that we have a second moment. So this is equal. This is something to watch out for also later on. When things get more complicated, we may have some uglier functions over here. So we have E, and then we have the expectation of T squared. Since there's no way we're accessing the correct constant anyway, this is okay, this is finite. And what's left is really just the probability that E is in the intersection of all geodesics between 0 and any one. Okay? Any questions so far? So if we summarize what we've obtained, we found that the variance is bounded by this, a constant times the sum of these probabilities. But if we just apply, what's it called, Fubini's theorem, we can rewrite this sum of probabilities as a sum of expectations of indicators, and we can move the sum inside, and we find that the variance is bounded by a constant times the expected size of the intersection of all geodesics. And now we see why ingredient B, moment bounds for the size of geodesics, is important. So this we would expect that this is bounded by n, right? A possible situation where it would be bounded by n is if you put a lower bound and upper bound on the edges, then the size of the size. So let me actually write. I think I've made this remark before. So if we assume that TE is bounded between A and B, and A here is positive, then the size of the geodesic between 0 and any one, or the size of the intersection of all geodesics, would be also bounded by B over A, I guess, times N. This, I guess, I'll leave you to think about this. It's fairly easy. But in general, we don't want to assume this. We want to allow for the possibility that the edge weights are arbitrarily close to 0 and also possibly very large. So we need an estimate for this expectation, and we want an estimate of order n so that we get a variance bound of order n. Yeah, on average, I don't know. Yeah, I'm not sure.
There's a result that says when that happens, which must be in the discrete case, that
All right, so thanks for that. So now let's look at our ingredient 2 and see what we can actually prove about this expectation. So ingredient B, sorry, the side of moment bound, ingredient B. Remember, I stated it as moment bounds for size of geodesics. And depending on the application, depending on the exact thing that you want to prove, you might need different bounds. But for us, what will be sufficient will be the following bound. We'll show that if we look at G, and I define this to be the intersection of all geodesics, its size. If I look at the expectation of that squared, I can bound it in terms of a constant times the passage time itself squared. And now the passage time, that one is clearly going to be linear. And why is that? Well, the passage time is a minimum over all possible paths. I can just choose a given path, say it's just a straight path, right? So this one is bounded by a constant times n, because T0 and E1 is always bounded by, say, the sum over edges, so let's say edges on the horizontal segment. On the horizontal segment 0 and E1. So it's just, let me draw it, but I think it's pretty clear what I'm saying here. You just take all these edges, the edge between 0, 0 and 1, 0, 1, 0 and 2, 0, all the way up to NE1. Okay, so along this path, we have some edge weights, but they're independent. And so this is a sum of independent random variables, right? So whatever they are, if we sum n independent variables, we're going to get something of order n.
Wouldn't you get something of order n squared if you don't subtract the mean?
Okay, so maybe I'm clear. So this is what I want to say, right? So this is what I want, right? I'm clear T is bounded by constant times n, so T squared will be bound by constant times n squared, but I'm looking at the second moment, right? If I have the second moment and I plug it into here, it gets square rooted, right? Is okay? All right, so let's see. Okay, so let me just write what I said. If we assume this result, we're done. So assuming star, we now have that the variance of T is bounded by a constant times the expectation of G, but that's bounded by a constant times the expectation of G squared to the 1/2 power. So this is Jensen or whatever you call this inequality. And that we're saying, according to star, is bounded by the passage time itself, and the passage time is dominated by this sum of ideal random variables, so we get what we wanted. Okay, so now comes the time for the lemma that was mentioned. What's the number of the lemma? 5.26. How do we prove? How do we get this? This is this lemma that was mentioned last time, and it's a lemma that says that basically if you have a long path, then it must actually have long path, meaning containing many edges. It must actually have a pretty large passage time. So you cannot somehow generate a small passage time by trying to push down the weights of the edges along a long path. So here's a statement. So the lemma, so this will be for star. And this is this lemma from Keston in aspects of first passage percolation that is extremely important and is an interesting blocking argument using, I guess exponential decay of in subcritical percolation of the cluster volume rate. Yeah. Sorry?
What you meant to say
Decay? No, I mean, it's a block argument that uses exponential decay of the cluster volume, I guess, below PT or P. Oh, okay. All right, so let's state it. So the probability that there exists a self-avoiding gamma containing 0. So those are the ones that we're interested in here. So the origin with G, so the size being bigger than n, so it has a lot of edges, but the passage time is small. So by this, I mean the sum of the TEs for E and gamma. The passage time is less than A, where A is, A times n is bounded by E to the minus Cn. So this says if you have a long path, long in the sense that it has a lot of edges, then the passage time must be over n. Okay, so how does this help us? So let's assume this for a second. I guess I'm going to assume it, and let's see how it actually leads us to this. Is the statement clear? Yep. Oh, 0, sorry. There should be this. 0 is the origin. For us, it's, I guess it could be. Yeah, so everything I've done so far is dimension independent, right? We can do it in any dimension. Okay, so let's assume this, let's call it double star, and see how it gives us star. Okay, so let's see how double star. Okay, so let's define Zn to be this G that we have over there with the indicator that the passage time from 0 to NE1 is smaller than A times G. Okay, so what does the double star say? Double star is basically just bound for the tail of Zn, right? Okay. So now, how does this help us? Well, remember what we want to do is we want to bound the size of G in terms of T. And this will allow us to bound the complementary event. So when is G a good bound for T? Well, that's when T is basically of the order, of the number of edges, right? Does that make sense? Okay, so if we start with expectation of G squared, we can split this as usual into two possibilities. Either we're less than this or we're bigger than that. Where either G can be bounded in terms of T or it cannot. And if it cannot, then we're dealing with Zn. Okay, so let's say G squared, and this is T is bigger than A times G, or the complementary event, which is that T is less than A times G. Right? So now, if I can bound G in terms of T, so when I can bound G in terms of T up to this constant A, then I'm home. I got what I want. In the first situation here, I get a 1 over A squared times expectation of T t squared, right? And then the second term is exactly this, right? But thanks to Krishnan, we can absorb this second term and just get a bound of order n squared. Is it okay? Okay, so let me just go. I see some hesitation. So first, what are we trying to do? We saw that if you assume basically that there's a lower bound and an upper bound on the edge weights, then the size of the geodesic deterministically is going to be bounded by order n. Basically because it doesn't make sense to go further outside of a box of size b over a times n if you're just trying to get over here, right? Because you can always, at the absolute worst, everything here is filled with the higher weight, and you can see that this is still going to give you a passage time of order n. Now we want to allow for the possibility that the weights can be very small or very large. But we are claiming that the size of the geodesic, so the number of edges in the geodesic, can still be estimated in terms of the volume or the time, okay? And this is going to be true if it's not actually possible for the passage time to be linear while this is very large, okay? And that's exactly what this expresses. It says, if you're large, if G is large, then the passage time also has to be large, okay? And then we implement this over here by saying, well, either the condition over there is violated, which is small probability, or we can actually bound G just in terms of T. And if we can bound G in terms of T, we've already said that T is just dominated by the sum of IIDs, so we just get N. Okay, so we have proved now that the variance is bounded by N. Let me just summarize the three ingredients that went into the proof, because those ingredients will just come back in a slightly, or the two ingredients that went into the proof, because those two ingredients will just come back again and again. So we have proved that the variance of T is bounded by a constant times N. And how did we do it? Well, we proved first, we showed, I called it Efron Stein, but there's other ways to go about it. Krishnan basically he didn't call it Efron Stein, but he did this Martingale decomposition that we used to prove Efron Stein. So we isolated the effect of every single edge. That already is, there's already a big potential loss there, but you can do it. So you can bound the variance in terms of a constant times the probability that E is in the intersection of all geodesics. And so then this reduces the problem of bounding the variance to the problem of bounding the moment, right? How did this work? This went through the linearization of the passage time, thinking about how the passage time can change when we change a single edge, right? Sorry.
Can you explain why you called it linearization again?
Well, T is a nonlinear quantity, and I'm looking at what happens when I make a small change, and this is a nonlinear function of any one edge weight, and I'm looking at what happens when I change it. And I replace it by something that's, E minus T prime times a condition. Yeah. So that was ingredient A. And so then we see that this guy is the same as a constant times the expected size of the geodesics, or the intersection of geodesics. And then our ingredient B, that was through this Krishnan lemma, our ingredient B was basically saying that you can bound G in terms of T up to a small error, probabilistic error, and then we found a constant times N. Okay? And this is basically all there is, at least at the current level of technology, to getting upper bounds for the passage time. It'll just be a small ingredient C that's basically just an amplification of B. That there is not just saying that the geodesics are linear in terms of size, but also that they're really one-dimensional. So when you cut them with sets, they also, they have the size of the intersection is what you would expect if a line cuts a set. Okay? All right. So this is what Krishnan did. How much time do I have? Okay, so this is what Krishnan did. What about the improvement? So I stated this improvement. So this was originally due to Benyamini, Philippe, and Efron. So they looked at the case where we have, I like to call it Bernoulli edge weights, but just in uniform, the edge weight distribution is uniform on two values, two atoms, A and B. So PE is uniform on AB. This is the theorem by Benyamini, Philippe, and Efron. And what do they say? They say that in this case, we can do a little better than testing, and we can improve the bound n to n over log n. But remember that what's expected is that it's actually n to some power less than 1. And in fact, Krishnan, I think at the end of one of his papers, he writes that the next challenge, and this was maybe 30 years ago that he wrote this, or 25 years ago that he wrote this, is that the big challenge is actually to get a 1 minus epsilon here. So if you're ambitious, this is a problem that you should look into because nobody really has any idea how to do it, and also anything you get would be a great result. So you can basically, anything you can think of, you can just try to throw it at this problem. So how did Benyamini, Philippe, and Schramm get this improvement of log n? They used a general fact that's a replacement for the an improvement of the Efron Stein inequality that we're going to use as well. Sorry, I have to find my notes here. They use, so replace the tool here. The tool for Krishnan bound was the Efron Stein inequality. The tool that Benyamini, Philippe, and Schramm used is one of the inequalities called Talagrand's inequality. It's not the famous Talagrand's inequality, but it's an inequality of Talagrand that he had in a paper called, I don't remember, maybe, an approximate 0-1 law, something like that. And what does it say? Same setting as before. We think of a function of many independent random variables. Here, we'll actually be in the finite setting because our weight distribution is in a compact interval away from 0. So we can think of the passage time as an honest function of finitely many random variables. And Talagrand gives us a general way to bound this. And what is it? He says that the variance of f is bounded by a sum where the denominator looks very similar to the Efron Stein inequality. He says, take the vector x. So here, I guess I should say that x is a Bernoulli vector. So this is x is equal to x1 up to xn, and each of these takes the values plus or minus 1, and the measure is uniform over all possible values. So we look at f of x minus f of xi, where xi is the vector that's identical to x, except that the I-coordinate is flipped. And this is squared. So this, if you think about it, is basically the same up to a constant than taking the difference between f of x and f of x, but where you replace the I-coordinate by an independent copy. But there's an improvement here. So there's a denominator that is potentially large, and that's what these guys here exploited. So we have 1 plus the logarithm of the difference between f of x minus f of xi, measured in the L2 norm, divided by f of x minus f of xi, measured in the L1 norm. Okay, so let me just clarify some of the notation here that I talked about verbally. first x superscript I is the vector where we flip the ith coordinate. So if I look at x, which is x1 up to xn, remember these are plus minus 1. So I can look at xi. This one is equal to x1, but then in the ith coordinate, I have minus xi. So this is the ith coordinate. Okay, that's our definition of xi. I flip the ith coordinate. Okay, and then when I write this here, when I write the L2 norm of x, I mean the expectation of x squared. I'll take that square root, and here this is x in L1, and this is expectation of x. Okay? All right, so how does this help us? How can the factor log of f of x minus f of xi help? So remember, if we didn't have this factor, then we would be back in the same situation as we had before. We'd just be applying the linearization, and then we'd be in exactly the same situation. So the only way that we can do better is if we basically have a uniform lower bound for this, and the lower bound will turn out to be logarithmic. Okay, so how can this help us? Well, let's think about what the linearization looks like if we look at the L2 norm here. So let's look at the denominator. If this is going to be large, so that we get an improvement, we have to compare the size of this denominator here to the numerator. So let's look at f of x1 minus f of xi1. And then by a similar type of argument that what we had before, we can bound this by f of x minus f of xi. But remember, these weights now are associated to, these Bernoulli random variables control the weight of the geodesics. A minus 1 is associated to A, and 1 plus 1 is associated to B. So this difference is only going to matter. It's only going to be non-zero if I'm actually in the intersection of all the geodesics, right? 0 and E1. I can put in this indicator, right? And now, since I want to compare the L1 norm, which involves just the expectation of the absolute value, and I want to compare it to the L2 norm, well, basically, the most obvious thing to do is just to use the Cauchy-Schwarz inequality. Okay, so I put this in L2, and this one is going to become a probability. Right? So I get expectation of f of x minus f of xi. L2, and this here is the probability that E is in a geodesic 0 to n E1 to the 1/2. Okay? Why are we doing this? We're doing this because we're hoping to get a lower bound for this ratio, right? And if we're going to get a lower bound for this ratio, if you look at this inequality, this means if I want f2 over f1 to be large, that means I want f1 divided by f2 to be small. That means I would like this probability to be small. Right? And I would like it to be small uniformly. Well, it's definitely small on average. That's this moment bound, right? Even though, let me write what I said. So we want the probability of E being in a geodesic. We want this to be small and preferably over n to the minus c. Uniformly, which would be great. If we had that, then we would be done, right? Then we would have a lower bound of log n here, and we'd be back in the situation that we already dealt with. Okay, so what's an indication that this might be true? Well, we already know that this sum here, probability E is in geo 0 and E1. We already know that this sum is equal to the volume of the intersection of all geodesics, and this is of order Cn, right? On the other hand, this sum here this sum has order n to the d terms. Yep.
Geodesics or intersection?
No, it was interesting. Remember that we had this picture. If you're actually in a situation where you can have more than one, then if there is a geodesic that doesn't go through E, then changing the weight at that point, changing it upward, is actually moves you to this other place. Okay, so here we have order n to the d terms. And why is it order n to the d? Well, that's again because of this the fact that we're concentrating on two possibilities. So actually, you can check that the only places the geodesic can be is in a large box of size b over a to the n, right? Okay, so we have a lot of terms and n to the d terms, and they sum to something that's less than n. Okay, so if all these terms were more or less the same, and if you just guess based on a picture, you'd say, oh, the probability goes through here and here, it should be roughly the same, maybe. Okay, so if all these terms were the same, that would indicate that the probability that E is in a geodesic from 0 to any 1 would be of order n to the minus d plus 1, right? That would be consistent with this inequality. Of course, it's only consistent with it. It's actually not really the case that this is uniformly true. Why is that? Well, if we think about edges that are very close to the endpoints, let me draw it over there so it doesn't get too cluttered. If we think about edges that are very close to the endpoints, so very close to 0 or very close to n, these edges, it doesn't seem very likely that you'd have a small probability to go through them, right? If I look at 0, 0, and E1, and I look at these edges, say we're in dimension 2, for example. If I look at these 4 edges, one of them has to be taken, right? So that immediately tells you that it's not going to be the case that all the edges have this upper bound for the probability that these geodesic goes through them. But these guys over here, maybe that probability would be small. Okay? Maybe it's of order n to the minus c for some c. So one of the problems to make this, and that's what Benjamin and Schwann faced, one of the problems to make this strategy work, and here strategy just means plugging this problem straight into this inequality, is that this upper bound is not quite true. Okay, so we need to replace it by something else. So let me write what I said. So close for E. So for E close to 0 or NE1, the probability that E is in Geo 0 and E1 is not small. But if you really want to do the most naive possible thing, which is to get a uniform lower bound for this and then apply the same thing we did, then you would need this to be true for every single edge, right? Because you can't allow this to be variable. What we've actually computed is the sum of these guys, right? Is not small. So the solution, there's two ways. One thing you can do is just change the problem. Okay, so there is one observation that I guess Jeff Steif made, and it's in these notes by Jeff Steif and Christophe Garbon, is that if we change the problem, and instead of asking for the first passage time between 0, 0 and NE1, we ask for the first passage time across, like in one direction across the cylinder. So we ask for the minimum passage time among all paths with winding number 1 in one direction on a torus. Then we actually have homogeneity. Every single edge is equally likely to be in that geodesic, and then we can just conclude. So that's just an observation. So, so one possibility is to change the problem. This is, I think, is in a paper of Jeff Steif, is you consider, instead of what we were looking at, consider T N to be the path with winding number 1 on along the first coordinate unit of a torus. So say, for example, in 2 dimensions, you have a torus like this, and these arrows mean I'm identifying the sides. Then you can look at the path that has winding number 1. So it goes around once in this direction. And we want among all the possibilities, the one that has minimum weight. For this function, there's no longer, this is delocalized now, as physicists would say, there's no longer any anchoring point, right? There's no longer this problem that the edges very close to the origin or very close to the endpoint have a special role. Every edge is the same. But if every edge is the same, we can go back to our observation over here that they sum to n, but they're n to the d of them. So every edge must have probability n to the minus d plus 1. Actually, in this case, it's an identity up to a constant. And in that case, we can just plug it in and get the result. So that's one solution, but maybe usually we don't we try to avoid changing the problem when it's possible. And so what Benjamin, Colin, and Schramm did is they averaged. How much time do we have? Okay. All right, so I guess we can at least explain this. Okay, so solution number 2 is the BKS averaging trick. So the actual averaging, what's the idea of averaging? It's to consider, instead of considering one problem of the passage time from 0, 0 to 0 to any 1, is to consider a bunch of passage times between points that are contained in small balls around the endpoints, and then average over those. Okay? And then if you ask, what's the probability that a single edge belongs, that a single edge actually matters for this average, this probability is going to be much smaller. Okay? The way that BKS, that Benjamin, Kalai, Schramm implemented this is actually somewhat complicated, but this idea of a geometric averaging, I think, appeared in a paper of Zigouras and Alexander on polymers. Okay, so what does it mean concretely? Let's look at, instead of the original passage time, let's look at the average passage time in a paper with Michael and Jack. We denoted by Fm, and what is it? It's going to be a sum, an average over Bm. So Bm here is going to be a square or a cube of size m. You look at a cube of size m in d dimensions, and we average the passage times between z and z plus ne1. Okay, so we take this, all the possible starting points in this box, and we look at the problem, but just shifted by z. Okay, so why is this allowed? So we think, okay, but you also changed the problem. But actually, we didn't, because we'll see that in a second. I'll tell you that this average, when we look at its variance or its expectation, is actually fairly close to the original problem. Close enough that we can replace our problem of estimating the variance by the problem of estimating the variance of this guy. And this actually I'll leave as an exercise. I'll put it on the worksheet or whatever. So this is Lemma, or yeah, I guess Lemma. This will be an exercise. If take m to be n to the quarter, and let's make it an integer, then if we look at the variance of our original problem, so 0 and e1, and we compare it to the variance of this guy, fm, we get something that is much lower than our target. So I don't remember exactly, but we get something like this, maybe even better, 3/4. Okay, so we get something that is less than n. So that means that when we want to, if we're just trying to show that this guy is less than n over log n, it's enough to show that this guy is less than n over log n. And what we've gained, remember, why are we doing this? We're trying to avoid this problem that the edges that are here or here have too large an influence on the size of this guy. Okay? So now, all right, but in practice, how do we implement this? We don't actually want, okay, so we don't actually want, eventually we will not want to restrict ourselves to the case of Bernoulli weights. So instead of using the Talagrand inequality, we're going to use a different tool, a third tool. So we found Stein and show you the Talagrand inequality. Maybe I'll put the Talagrand inequality on the worksheet too, because BKS found a nice proof of this. We'll use a third tool that was developed by Philippe and Sabornitsky. Actually, Sabornitsky is at Cornell. So I know him, even though I'd never met him then, I see him every week now. So that's a piece of trivia. Okay, so we need a third, we're going to use a third inequality that also works very well in this Bernoulli case, but can be extended, and that will work very well with this averaging. So again, same setting. Say we are looking at a function from Rn into R, and f is a function of IID random variables. So f of x1 up to xn, and these guys are IID. Then the variance of the function f, this is what we want. And then there's an extra factor that will help us get to our result eventually. It's a log factor, so that looks good. And we have a sum over I of the expectation of delta I of f. Maybe I'll just write it as delta I to match our notation from before. We're saying that this is bounded by a constant times the sum, or maybe it's actually just the sum of expectation of f of x minus expectation of f of x prime squared. Okay? All right. So here the delta I, you have to, no, I can go on. Okay. Sorry? Yeah, the square is inside. All right. And here delta is as before, it's expectation of fi minus expectation of fi minus 1. Okay. So do I have 5 minutes or? Okay, so let's assume this inequality. So at this point, I think this is maybe 4. We've already had triple star. So let's assume 4. And this guy. And finish the proof or discuss how the proof might go. I guess I'll repeat this at the beginning of the next lecture. So for the proof is in a couple of steps. Number 1, let's look at the right side here. The right side, let me call this right-hand side. The right-hand side, because we're working with Bernoulli weights, let's look at Bernoulli weights to simplify our lives. The right-hand side is just going to be bounded by the size of the geodesic, and that one is bounded by B over A times N. Okay, so the right-hand side, no problem. And then we're going to use we're going to try to estimate these guys here with F being equal to the average FM. Okay, so we look at expectation of delta I FM, and we just take, we use the triangle inequality and Hanson, and we replace this by 1 over, sorry, we just use the triangle inequality first. We replace this by 1 over Bm times the sum over Z and Bm. That's because that's what the average is. If you look over there. And then we have delta I applied to T between Z and Z plus N E1. Okay? And now this guy, we can treat using the linearization as before, and replace it by a sum over the probability that EI is the geodesic is the intersection of all geodesics between Z and Z plus any1. Okay. So since I'm going to repeat this anyway, let me just write it over here. So this will be bounded by the sum over first an average over BM, Z and BM, and then the sum over over the edges that the probability that sorry, this is EI, so this is actually, there's an edge here. This is the edge EI is in the geodesic from Z to Z less n E1. If we now took the sum over I inside here, we will be looking at the the size of an intersection of the geodesic with this ball here, right? And this size will turn out to be linear, or it will turn out to be linear in the diameter of BM. So that will say that the geodesics are one-dimensional, and that's what will allow us to take advantage of this averaging. Okay? So it turns out when we sum over E, that this will be linear in the diameter of BM, but we're dividing by the volume of BM. So that's how we're going to get smallness for this guy. If we have smallness for this guy, we get a small factor here, and then we're home. So I guess it's better for me to do it. It's better if I stop here and do this in more detail next time. But as you see, in every case, we have basically a general tool that allows us to go from the variance to a sort of linearization of the variance, where we isolate the effect of a single edge. This is already very messy. If you think about it, this is part of the problem of where we're stuck at n. But once we have this, we've seen two inequalities, Talagrand and Riedhipratim and Philippe, that have an improvement. And this improvement required you to be able to show uniformly in the edge that a single edge doesn't have a big effect. Okay, so the probability that you go through this edge is small, so it's unlikely that changing this edge weight is going to have an effect. And this is translated for Talagrand, it's translated by this ratio of L2 to L1. And here it's translated by the fact that we have this sum of the delta i's in the denominator, and that we can show that we get something small. So we're going to finish this next time. Thanks for listening. Any questions? All right, thank you.